Hello everybody and welcome to today's video. Today we'll be going over chapter 4.2 of Calculus and Vectors. So today we're gonna find out what the derivatives of the sine and cosine functions are. In order to do that, we're gonna first of all talk about the basic procedures that we need to know, and then we're gonna summarize the main concepts that you'll need for the remainder of the chapter. So here are the basics. Essentially, what you must memorize is that the derivative of f of x is equals to sine of x would be cos of x. And the derivative of cos of x would be negative sine of x. If you remember these two equations, you will be good to go with the remainder of the chapter. The rest of the concepts that are covered in chapter 4.2 is simple algebraic evaluations that we could do with the derivatives, some simple laws that we could apply, and also of course how we figured these two derivatives out. So in case you want to skip the whole proof, we'll leave a timestamp in the description as well as show it on the screen. So feel free to skip to that now. So for those that decided to stay, here is the algebraic proof of these derivatives. So to figure out this proof, you will need the compound angle formula that we learned in advanced functions, and then you'll also need to recall the first principles definition of a derivative. So if you remember those two things, then you'll be good to go with this proof, except for like one little part that I'll show you. So remember that this right here is the first principles definition of a derivative for the function of sine. Because remember, the normal one, it would be f of x plus h minus f of x divided by h, right? And then we're taking the limit as h approaches 0. So using these two, as you can see, we have sine of x plus h. We know what that equals to, so we could plug in the compound angle formula for sine into our equation. So now we get this following expression. We could tell that we have sine of x in both of these terms, right? So we could actually factor out sine of x from this side over here and this side here, which is where we get this expression. And then we're left with this part. So now we have sine of x times cos of h minus 1 plus sine of h times cos of x, all divided by h. So here we could just apply our fraction rules that we know from like grade 8. If we want to split these two up, we just have to have them over the same denominator. So now we could have sine of x times cos h minus 1 over h plus sine of h times cos of x over h. This right here allows us to distribute the limit, right? Because we've learned the limit rules in chapter 1. So now using that same knowledge, we could apply it here. So now instead of taking the limit of this huge expression, we're taking the limit of the two smaller expressions and adding them together. So what do we notice in common between these two things? Well, we have sine of x on this side and cos of x on this side. So we could technically just factor them both out. We're not changing anything in the equation, we're just rearranging how it's written. We could also take the limit of the inner parts as well, since using our limit laws, we know that we could just multiply it by a factor, which is what we did here. So this part is what we don't know yet. We don't know how to evaluate cos of h minus 1 over h, and we don't know how to evaluate sine of h over h. So I could give you the answers. It's 0 and 1 respectively. So if you could memorize that, that would be good. But if you can't, you could also just try and use your limit strategies, right? So you're going to approach it from the left hand side and the right hand side to evaluate the limit. So over here, for example, choose 0.001, and this also 0.1. then evaluate the limit there, then evaluate the limit from the negative side and see what they're approaching to. Either way, you'll get to the same answer of 0 and 1. So now sine of x times 0 of course equals to 0, and so we're now just left with cos of x. To find the other derivative, you could also use the exact same procedure but now for cos of x. In this case, you'll need to know the compound angle formula for cosine instead of sine, but again, everything else is the same. You could also use the following proof that we have here to determine the or to prove the identity. So we have the fact that cos of x is equals to sine of pi over 2 minus x. So we just shift it and we get cos of x, right? That's what this means. So now, using the derivative of sine of x that we just proved, we get the following expression. So the derivative of cosine pi over x times the derivative of pi over 2 minus x is equals to this. So we have sine of x times negative 1, which gets us to negative sine of x. So in case you're wondering why this expression right here works, well, it's actually a little bit tricky, but I'll still explain it. So as you can see here, we have sine of pi over 2 minus x. We could treat this as two separate functions. The first of all, we would have the function sine of x, so that's the outer layer, and the inner function would just be pi over 2 minus x, right? So now we have a chain of functions. So we have f of g of x, which would mean we could apply the chain rule. So how do we apply the chain rule in this case? Well, we know what the derivative of sine is. The derivative of sine is cosine. So the derivative of the outer function would be cos of pi over 2 minus x. So we have that part down. Now we need to find the derivative of the inner function. So the inner function is pi over 2 minus x. Pi over 2 minus x, the pi over 2 is a constant, so that would just disappear once we take the derivative, and then negative x turns into negative 1. Here we also know that this would just equal back to sine of x, so now we get our sine of x times negative 1, which gets us our negative sine of x. So as a quick recap for this part right here, this would also appear in this formula here if you take this route. If you want to make sure that these functions do actually go to 0 and 1 respectively, you could actually graph them on decimals like I did here, and as you can see, as we approach from the left and the right hand side to 0, we get 0 here, and as we approach from the left and right hand side here, we get to 1. So that is the reason for why these functions, although if we try to plug anything in them, would result in a form of 0 over 0, they actually do have a limit that we could find algebraically in a way, not right now, but definitely we could find it graphically. So now that we have that, we can move on to the main concepts that we need to know. So since we've just learned two new derivatives, we must learn how to perform all of the operations that we did before. So that includes knowing our multiple rules, our sum and difference rules, or how to find a slope at a point, and the equation of a tangent line, stuff like that. So as a quick recap, the constant multiple rule just states that the derivative of y is equals to c times f of x is equals to c times f prime of x. So you could take that constant out, take the derivative of the function, and then multiply it back. So of course, this identity is, or this property is still true for sinusoidal functions because they are indeed functions. So in our example here, we have f of x is equals to negative 9 cos of x. So if we want to find the derivative of that, we could take the negative 9 out, so leave it out here, and then take the derivative of cos of x, which now we know is negative sine of x. So multiplying the two, we get 9 sine of x. Also, we need to recall our sum and difference rules. So remember that if you take the two functions f of x and g of x, you could find the derivative of the sums of them by simply finding the derivative of f of x and the derivative of g of x. And then just do a procedure. So if you're doing sums, you add them. If you're doing differences, you subtract them. So if f of x is equals to 6 cos of x and minus 11 sine of x, then we could take apart these two here. So this would be our function 1, this would be function 2. So the derivative of function 1 would be negative 6 sine of x, and the derivative of function 2 would be negative cos of x. And that is what f prime of x equals to. To find the slope at a point, you would need to find the derivative at that point. And then you'd substitute the given point back in to find the slope. So what do I mean by that? Well, if you have f of x is equals to 4 cos of x, we need to find the slope at x is equals to pi over 3. So this is quite simple. The derivative of this would just be negative 4 sine of x. So now we will substitute our point back into f prime of x now. So f prime of x is equals to negative 4 sine pi over 3, which is giving us the value of negative 2 square root of 3. So this right here would be the slope. If you want to go further and find the equation of the tangent line, you would need to find the slope at a point first, then you'd substitute the value here into m, you'd substitute your x and y coordinates, which would be given to you in the question, and you'd solve for b. Then you'd write out your equation in the format of y is equals to mx plus b. So if you have all of those concepts down, you are now done with chapter 4.2. The remainder of the chapter will be talking about other rules that we have to apply to sinusoidal functions. So again, chain rule with big sinusoidal functions. So not just sine of x and cos of x. Maybe it'd be like sine pi times 6 pi minus 3, stuff like that. But we'll go over that. We will also do chapter 5 soon, so I hope you're excited for that. One of my viewers brought up the fact that they're starting chapter 6 soon, so they're skipping over chapter 4 and 5. So if that's the case for the majority of you, I might do that also. I'm thinking of finishing off chapter 4 at the very least, but hopefully I could get through chapter 4 and 5 within like the next week, and then like hurry from chapter 6 to chapter 8, so like one upload a week. That is currently my goal. I really want to make sure I'm done before people enter quad 4 for those that are in the quad system right now. But yeah, hopefully you all enjoyed today's video. It was a pleasure to teach all of you, and I hope to see you guys next time. Bye bye!